This show me is just to cover levers, first, second, and third class levers, as well as do a quick overview of the moment calculation when static equilibrium occurs. First class levers. All three of the below pictures are examples of first class levers. We have one that has a mechanical advantage of 1. We have one that has a mechanical advantage greater than 1, and another that has a mechanical advantage less than 1. Two things to keep in mind about first-class levers is that the fulcrum is located between the resistance and the effort forces. Fulcrum in these is identified by the triangle. Also that the force of effort and the force of resistance are applied in the same direction. This is the only class of levers that this is true. As far as what the effort force is, on each of these levers, my effort force is identified by the green arrow. And I'm writing the FE next to it because it stands for my force of effort. The resistance force is labeled as FR, and that stands for force of resistance. These hold true on all the different types of simple machines, not just on levers. We also have the distance between our fulcrum and our effort, and that's my distance of my effort. The distance between my fulcrum and my resistance is my distance of resistance. So on each of these different levers, I have my distance of resistance and my distance of my effort. That's from the fulcrum to the effort, or from the fulcrum to the resistance. E standing for effort, R standing for resistance. First-class levers are also the only type of levers that can have a mechanical advantage of 1, greater than 1, and less than 1. And if you remember our definition of mechanical advantage, if it has a mechanical advantage of 1, for all the force I'm putting into the machine, or the lever in this case, I get the same amount of force out as far as into my resistance. Mechanical advantage of greater than 1 means for over a much longer distance, I use less force to move about the same amount of resistance. For mechanical advantage of less than 1, I put in greater force over a shorter distance. Our next class of lever is a second class of lever. For a second class lever, the force of effort and the force of resistance are in opposing directions. The resistance in this case is between the fulcrum and the effort. If you remember from the previous, the fulcrum is the triangle. Our effort is moving up. Our effort force is moving up, and our resistance force is moving down. Best example of this is going to be your wheelbarrow. You put all the weight on the inside of the wheelbarrow, you lift it up, that's your effort force, and you're able to walk around and move the weight around. Your fulcrum would have been your wheel. For a second class lever, your mechanical advantage is always greater than 1. Remember, to have a mechanical advantage of greater than 1 means you're putting in less force over a greater distance, meaning I lift up with less force than what is going down into it, but I'm also further away from the fulcrum. So that's greater distance, less force. For the third and final class of levers are our third class levers. The force of resistance and the force of effort are both once again in opposite directions. However, now our force of effort is between the fulcrum, once again our triangle, and our force of resistance, which is at the end of the lever. Best example of this would be just a set of tweezers that you see. The mechanical advantage of this type of lever is less than 1, meaning I put in a lot of effort, or more effort, over a much shorter distance. So I have to put in a lot of effort in this area here, because it's much shorter, for a smaller amount of resistance force over a much greater length. To deal with moment calculations, you have to know that the item's in static equilibrium. To help explain what static equilibrium is, I've drawn a first-class lever with a force of resistance on one side and a force of effort on the other side. So that you know everything's equal. There's no movement in this lever whatsoever. It's standing flat. The only way this occurs is if it's in static equilibrium. Well, to have static equilibrium true, I have to have my distance of resistance labeled here. We'll do my distance of effort labeled here. So MR, or my moment of resistance, is equal to my moment of effort. For my moment of resistance, I just have my force of resistance times my distance of resistance from the fulcrum, and set that equal to my force of my effort, that's the energy or the force I'm putting into the system, times my distance of the effort from the fulcrum. The only way static equilibrium can occur is if these things are all equal to each other. Let's go ahead and look at an example. Here's an example of a first-class lever with our effort force, our resistance force. Since this is the distance of my effort force from the fulcrum, that will be labeled as dE. The item I do not know at this point in time is my distance of my resistance force. To find the distance of resistance force, I just need to do the lever moment calculations at static equilibrium and solve for dr. So to start off with the formula, so since I know this is in static equilibrium, my formula is dE times Fe, or my distance of my effort times my force of my effort, set that equal to my distance of resistance times my force of resistance. So now I just need to plug it. So I've gone ahead and plugged these in, and instead of writing just 36 2/3, I've substituted the decimal version of 2/3 as 0.66 repeating. Go ahead and do the multiplication here. Once I have the multiplication done on both sides, I have that 82.5 is equal to 36.66 repeating times dr. The final step to find out what my distance of resistance is to divide both sides by 36.66 repeating. The answer that I get is that dr is equal to 2.25. And since I was looking for a distance, it's 2.25 inches. We can do moment calculations with any of the 3 types of levers, or any of the 6 total simple machines that we've been dealing with. We do them in the exact same fashion, with the exact same formula that we use for the first class lever.